Okay. Hello, everyone. I'm Wanli Chen from the Chinese University of Hong Kong. Today, I'm very pleased to introduce our research work, efficient point cloud analysis using Hilbert curve. Let's review the background of point cloud analysis. Previously, the main approaches of point cloud analysis can be divided into two categories: voxel-based method and point-based methods. Voxel-based method keeps the locality of point cloud while the computational cost is very high. Point-based methods, on the contrary, has lower cost but with better spatial locality. Currently, researchers combine voxel-based methods and point-based methods together for better performance. However, the computational problem still exists. In this work, we propose to use 2D convolution to handle 3D data such that we have lower computational overhead and we can apply many useful techniques to increase accuracy, such as transformer. The question is how to map 3D data into 2D space. Here we apply Hilbert curve. Firstly, Hilbert curve has no jump connections, which leads to better locality. And also it has smaller space to linear ratio with better clustering property. Then let's move to our approach. The main framework is shown here, which has two branches, image branch and point branch. The framework HI, HA, and HP represents Hilbert interpolation, Hilbert attention, and Hilbert pooling, respectively. I will introduce them later. We first flatten voxel data into 2D using the voxelization and Hilbert flattening module. As shown here, it flattens the voxel data along z-axis. Then let's see the interpolation module, which is used to combine 2D image with 1D point clouds. We first review the trilinear interpolation process, which consists of a reshape function and an interpolation kernel. However, this process emphasizes the empty grid and the reshape function is not locality preserving. To overcome the two problems, we propose Hilbert interpolation, which has a weight to emphasize the non-empty grid, and the reshape function is replaced by the Hilbert flattening, which is locality preserving. Then let's see Hilbert pooling module. It combines 3D max pooling with Hilbert curve, which collects local information from original shape. The final module we propose is Hilbert attention. It collects inter-slice correlation, intra-slice correlation, and mixed correlation of 2D flattened voxels using attention module. Then we see some experimental results. The visualization of some results on S3DIS dataset can be found here. It shows that Hilbert net is much more accurate and applicable to large point cloud datasets. The detailed performance can be found here. Also, Hilbert net outperforms other methods on small datasets such as ModelNet and ShapeNet. Then let's see the inference time. We provide 3 different Hilbert nets with different channel numbers. It shows that Hilbert net is much faster than previous voxel-based methods and point voxel methods. Finally, we show that Hilbert attention is much more lightweight than 3D convolution and 2D convolution, even much more lightweight than sparse 2D convolution. That's all for my presentation. Thank you for listening.